the presentation. So please turn off your video if you do not want to be recorded. And so today our first speaker is Guang Yang. So Dr. Yang is currently a postdoc at Texas A&M University. He obtained his PhD in 2019 at Penn State University, working with Neil Brandt. He then had a summer visit to France, LAM. After that, he became a postdoc at Texas A&M. He is a major developer for the ICD fitting code, CIGALE. He is also an active member of the CERS, CEERS, an approved JWST program team, where he is the leader of the MIRI subgroup. His research interests include black hole galaxy coevolution, multi-wavelength surveys, especially Xray and infrared, and infrared instrumentation. So today, Dr. Yang will tell us about CIGALE, a versatile code for ICD fitting. So the floor is yours, Dr. Yang.
Thank you very much, Xray, for this very nice introduction. Let me share my screen. Hey, hi, everyone. Nice to meet you. And I'm Guang Yang from Texas A&M. And today I'm very happy to share with you guys about our ICD fitting code, CIGALE. And so what is CIGALE? CIGALE is a stand for Code Investigating Galaxy Emission. It's really a powerful ICD fitting code developed by our team. And on the left, you can see it's a logo of CIGALE. Of course, CIGALE is a French word that means cicada, this insect, you must know it. And from the logo, you can see there is UV, infrared, and that stands for CIGALE really keeps the energy budget. In CIGALE, the energy observed in UV is always re-emit in the infrared, so the total energy is conserved. That's what the logo indicates. And CIGALE is a symbol, this insect is a symbol of Provence, France. And it's where the code is born, is in Provence, in the Lam Institute. And CIGALE also have a good meaning in Chinese culture, and it symbolizes rebirth, immortality, and purity, especially in Asian and Chinese culture. And for our code, CIGALE, it really has a long history. Actually, I think it has a 20 years history to now. And the first formal paper is in 2005. And it's the original paper code was written in Fortran, but now we have rewritten CIGALE in modern Python 3 code. And it's open source, so everyone can edit it. And it's easy to modify to satisfy your own purpose. And as I said, CIGALE always build physical models that always keeps energy conservation. That's very good, good behavior of CIGALE. On the right-hand side, you can see it's a very nice ICD fitting that has many components for this galaxies. And the CIGALE is also very efficient, and you can run it on your own desktop or even laptop with a very typical Intel i7 or 9 processor. You can construct hundreds of millions models even within a few hours. That means you can deal with a large data set even using your personal computer. So it's very convenient to use. Also in CIGALE, we not only have the main program, we also have have some tools like plotting tools, and also we support the PEEP installation. Also, the configuration is very easy to read, so you don't have to read additional documents. The configuration has everything self-contained. So, but previously, one weakness of CIGALE is that it cannot model X-ray wavelengths. So we started a project called Xscale. We aim to extending CIGALE to X-ray wavelengths. So we started this project Xscale, and to develop an X-ray model to allow it to fit the to the X-ray wavelengths. The reason why we do it is that the X-ray is really a very sensitive, very pure tracer of aging activity. And for most of the X-ray detected sources, and actually in medium or shallow depths, you will see most of the sources are actually AGNs. Of course, we also account for galaxy emission in X-ray, but it's a minor component. And in the Xscale project, we also introduced a physical clumpy Taurus model. And also we allow polar dust obscuration for type 1 AGNs. So those are general improvements to the AGN module. And first, let's talk about the X-ray module. So in CIGALE, of course, we need to properly connect the X-ray to other multi-wavelengths data. So what we do here is we adopt the very famous X-ray UV relation, and formally it's called alpha OX L 2500 luminosity relation, and we think we consider this relation might be the most fundamental relation in the AGN. It represents some fundamental connection between AGN accretion disk and the corona properties. And we implement this relation, X-ray UV relation, to CIGALE so that it can connect X-ray property to other wavelengths for the AGNs. Of course, not only AGN have X-rays, but the galaxy may also have some weak X-ray emission. So we also need to deal with X-ray from galaxies. We consider both X-ray binary emission and also hot gas emission from the galaxies. And we model them as a function of stellar mass, star formation rate, metallicity, and stellar age. And the recipe is from this Fraggle's 2013 paper, and the recipe has been well tested by observations. And to see the power of the X-ray SED fitting, and here is a very good example. On the left-hand side is our fit with X-ray data, and you can see on the leftmost points here. And with the X-ray data, you can see this is actually a it's actually a very weak AGN. It's a bolometric luminosity only 10 to the 43 per second. And in the infrared, the SED is totally dominated by the star forming process. And but if you do not have the X-ray data, you fit only the UV to infrared data. It's very easy to get the AGN galaxy decomposition very wrong. And on the right hand side is a fit without the X-ray. You can see that the decompose into a very strong AGN emission and to the bolometric luminosity of 45. So this more than 2 orders of magnitude overestimate the AGN emission in the infrared. If you consider infrared correct, you plot the expected X-ray emission, you can see it's much higher than observed. So without X-ray, there might be a very strong degeneracy in the infrared. That's because both AGN and the star forming process can produce infrared emission very strong. But with the X-ray, the AGN has much more powerful than the star forming process to produce the X-ray. So the X-ray really breaks the degeneracy of the SED decomposition. So CIGALE is not only powerful in doing the SED fitting for the X-ray detect sources, most of them are AGNs, but it's also very powerful, very useful to perform SED fitting for X-ray undetected sources. This is super helpful because for typical X-ray surveys, only a few percent of the optical or infrared sources can be detected in X-ray. For the majority of the population of galaxies, they only have X-ray upper limits available. And fortunately, CIGALE can also use this upper limit to put very tight constraint for the AGN component. And this figure shows we tried the X-ray upper limit for 100 galaxies in the Akari NEP field with a very shallow Chandra exposure of, I think it's about 100 kiloseconds. So it's relatively shallow. And And you can see, even with this shallower constraint, after applying the X-ray upper limit, we can still have sort of a constraint on the aging fraction, the fractional aging luminosity in the infrared. We can still have some constraint. But if in the future, fortunately, we will have a CINA launch in the 30s. By that time, even with the 100 kilosecond exposure, we can reach the depth of the Chandra diffuse source deep of Chandra with a very shallow exposure of a CINA, only maybe 100 kilosecond. So what if we have a CINA upper limit? So here we have an experiment is that we replace the Chandra upper limit with the CINA upper limit, which has the orange points. And with the CINA very tight upper limit, we can almost rule out the possibility of aging for these galaxies. All the aging fraction are tightly constrained to essentially 0. So in the future, even you have a relatively medium exposure of CINA, you will put the upper limit of aging to a very low level. You can almost rule out the possibility of aging. So this is good if you want to focus on your studies on the star forming population. CINA will be helpful to rule out the possibility of aging. And yeah, as I said, we not only extend to the X-ray wavelengths in our Xscale projects, we also implement a Taurus model, which on the right-hand side is a clumpy Taurus model, which is a modern recipe called Skirter model. And the previous CIGALE only supports a smooth model of Taurus. Of course, we know this will be unphysical because the temperature will be too high to sustain such a kinematic structure of Taurus. The temperature will be higher above the dust temperature, the physical dust temperature. So we implement a new clumpy Taurus model for this. And we know the third thing we implement in Xscale project is to allow for a polar dust emission for the AGN. Here is a cartoon for it. Here Taurus, here above is the polar dust. The motivation is that from the local observation in the infrared, we see there are a lot of dust emission in the polar region. So we have a very dedicated, very good paper in studying the polar dust using CIGALE, the new version of CIGALE. So we found that here is a color plot. The dashed line is for the classification between red quasar and blue quasar, and left is blue quasar. You can see that if without the polar dust emission, most of the models are almost all blue quasars. You cannot produce red quasar without the polar dust emission. So this suggests a red quasar is motivates the polar dust component. So from our fits, we found that half of the strong quasar have the polar dust emission, and among them, about 60%, which 60% of them prefer a steep extinction curve. We use SMC curve. A minority population of 40% prefer a flat curve. We use the Xscale 2004 recipe. The red point is SMC. The Xscale flat curve is the green points. We recently have a new update for CIGALE. We call it have a new release called version 2022. In this release, the major thing we do is to extend the aging emission to the radio, because previous CIGALE only have star forming activity radio emission, both thermal and synchrotron, but those are all star forming, and it misses the aging emission in the radio wavelength. So we extend to radio wavelengths. Our recipe is using the famous R parameter, which is a free parameter in our configuration. It's a radio luminosity divided by the intrinsic UV luminosity. And we allow for a power law with a flexible index in CIGALE. And in the latest version 2022, we also introduced some new features, including X-ray anisotropy, flexible aging disk continuum slope, also flexible X-ray binary recipe. And for now, we think the code is very complete now because it can simultaneously fit radio wavelengths all the way to the actual wavelengths SED. So we really need CIGALE to have a comprehensive picture of the AGN and the galaxy activity. So we tested this new radio module on the Cosmos data. And because the Cosmos have a really good radio BLA 3 gigahertz data, very deep, also multi-wavelength data from X-ray to infrared. And on the left, you can see the old version of CIGALE without the AGN emission. You can see in many cases, the model radio luminosity 3 gigahertz is significantly underestimate the observed radio luminosity, radio flux. That suggests that we really need an AGN component to fill the gap between the model and observed flux. So if you run the new version of CIGALE, you can see the model flux can match the observed flux really well. And so it's quite successful after implementing the AGN emission in the radio. And from our statistical study, we found about half of them have a significant radio AGN component. So without the AGN component, you will mess up about half of those sources. So it's very necessary to have the AGN radio emission if you want to fit the radio data. You cannot assume most of the sources do not have radio. And here is a specific example demonstrating the usefulness of the radio module of the AGN. You can see on the left is the old version fit without the AGN radio emission. Not only the radio part is not well fitted, but also in the infrared part, the Galaxy is forced to have a very strong infrared Galaxy component. And the estimated star formation rate is 40 solar mass per year. But if you fit with the new version of CIGALE, which have the AGN emission, the radio part is well fitted, but also the infrared part is more accurately decomposed because it's not affected by the radio anymore. And the Galaxy actually have played a very minor role in contributing to the infrared flux if you have proper AGN component in the radio. The new estimated star formation rate is only 5 solar mass per year. So the difference is almost 1 order of magnitude. So without the AGN radio module, you might mess up with your star formation rate estimation. So you really need the AGN emission in the radio to have a reasonable estimate in the star formation rate. So here we play with the Cosmos data, which is from the radio all the way to the actual wavelengths to demonstrate the diversified population of the AGN. Here I show some examples. On the left, you can see the so-called radio galaxy. We would classify the radio galaxy. That's because these sources have weak X-ray, weak optical infrared of the AGN, but the AGN is only strong in the radio wavelengths, so it would be classified radio AGN. And on the right-hand side, you can see both of the radio and X-rays are strong in terms of AGN component, but the AGN is weak in the optical infrared. So we would classify it as radio loud X-ray AGNs. Now here are two other examples. On the opposite side, they have a relatively weak AGN radio components, so they would be classified as radio quiet AGN. And but on the left-hand side, this one is very strong in the X-ray. They will classify radio quiet X-ray AGN. But on the right-hand side, they have weak undetected X-ray, but very strong in the optical infrared. So we would classify it as radio quiet mid-infrared AGN. So this, for example, really suggests that we really need a multi-wavelength sensoring if you want to get a complete census of the AGN. And because some of the AGN is strong in the radio, some of them is strong in the X-ray, some of them is strong in the optical infrared. So you really need a full SED from radio to X-ray if you want to have complete sample of the AGN. But fortunately, in the future, we will have lots of good multi-wavelength surveys upcoming. And we will have Theta for the Xray, also Athena for the future. And in the optical, UV optical, we will have Xuntian or China Space Station telescope with UV optical, also very wide surveys of almost 20,000 degrees square. We also have Rubin for the entire southern sky. In the infrared, we will have Euclid and the James Webb. So that will give us very deep or wide infrared data. And all this can be used in CIGALE to perform cutting-edge aging and galaxy science. Also for the radio is a very exciting field because radio is really developing really fast. And actually the radio becomes so powerful and so sensitive, and they are not only the traditional sense of radio arrays, but they are more and more like the radio telescope. And because the surface density become very, very high, and you will have a very good resolution, arc-second scale resolution for those big arrays. And there is a low-far survey, and which is ongoing. The ultimate goal is to get the entire northern sky radio surveys. And actually, we have a paper using low-far and multi-wavelength SED based on CIGALE to study their properties, and our work in preparation. And in the future, there will be also several radio arrays, very exciting. In the United States, there will be DSA 2000, it's the low frequency. There will be also NGVLA, this higher frequency. And for the international program, there will be a super exciting Xscale. It's a very wide frequency band. So that's all I want to talk about today. And to sum up, and CIGALE is, we think it's the only powerful SED fitting code that can model radio wavelengths all the way to the X-ray wavelengths, including both aging and galaxy component. So it's very useful. If you have a SED data, feel free to try it out because it's so helpful. I think it's much more powerful than empirical template, because previously, due to the lack of a code, people often use empirical aging template to change the normalization and see how they match and do discussion. But now we really have a powerful code to do these things very quantitatively, and it will give you all the properties very easily in the output. And from the test of the Cosmos data, we really found the drive of using the multi-wavelength censoring of the aging, because some different aging have different strengths in different wavelengths. So if you want a complete sample of the aging, you really need a broad wavelength coverage to cover all the features of the aging. And in the future, it's very exciting because CIGALE is really good to apply to the big survey data from X-ray to radio telescope, including Athena, Xuntian, Euclid, LOFAR. All those will be helpful in helping us to understand more and more deeply about the aging galaxy evolution in deep space. So I really encourage you guys to check out our website, which is here. And you just Google CIGALE, it will pop up, I think. And in the website, we have the latest release, including both the formal release and the developing version of CIGALE. We also have discussion forum. There will also help desk. And yeah, feel free to visit our website and try it out, because it's really a useful code, especially for the future where when all the survey data are coming along. Yeah, thank you for listening. I'm happy to take any questions.
Thank you very much, Dr. Guang.
Sorry,
Dr. Yang. So is there any question so please?
So my first question is, looking at all of your plots, I don't think I saw any upper limit data. So what does the program do with observational upper limits?
Oh, I don't include here. And For the upper limit data, basically it have the full statistical way of dealing with it. It's a statistically very rigorous way. For example, if you have the Xray upper limit here, if you put the upper limit here, and it will basically remove all the models that's above the Xray upper limit constraint. So it will only allow models that's below this upper limit. So that will give you a very good constraint on the AGN component. For example, here if you apply a thin upper limit, because all the models that have the AGN component will produce detectable X-ray emission, which is incontrovertible with the thin upper limit. So in this way, CIGALE can really put a quite strong constraint on the AGN component. For example, if you have the X-ray upper limit. Although I don't have a plot here, but it's what CIGALE actually does.
So do we have further questions? So I saw Matthew, you can unmute yourself.
Thank you. Can you hear me?
Yes.
Okay, thank you. Thanks for a great talk. I had a question about one of the technicalities. I think Lori Chesla might have published a paper describing a much earlier version of CIGALE in which she claimed that the ability to distinguish the degree to which the AGN contributed to the bolometric luminosity of the source was about 15% there or thereabouts. And I was wondering if you could comment on like the floor at which Xscale might now be expected, the precision with which Xscale might be expected to identify the contribution of an AGN to the SED of, a luminous, well-characterized galaxy.
Yeah, it's a really good question. Actually, that's depending on specific sources. In terms of the fractional AGN, this is a good example. On the left-hand side, you can see, I guess for this sample, the AGN component in terms of bolometric luminosity is only a few percent. So because maybe less than 1%, because in the infrared, its source is totally dominated by galaxy, not AGN. AGN is only prominent in the X-ray. So for this source, this is a good example showing that how usefulness is Xscale. Although to clarify, for now, CIGALE has all the capability of Xscale. We merged the two codes together in our latest release. So for these sources, we can go very deep. That's because you have the good X-ray data. I think this data is from Chandra Deepfield source also, and the X-ray is very good. So it can give you a very deep AGN detection, even though the AGN is only about 1% of the bolometric luminosity. Yeah, but the specific situation varies from source to source, and depends on how depth of your X-ray surveys.
That makes sense. Thank you very much.
Yeah, thank you.
Do we have further questions in the conference room? And thank you, Dr. Yang. Let's thank the speaker again.
Thank you. Yeah, thank you very much.
So our next speaker is Dr. Marco Ajello. So Marco, if you can share your screen. Oh, thank you. So Marco is an associate professor in the Department of Physics and Astronomy of Clemson University. His research focuses on the origins of cosmological backgrounds and the evolution of massive black holes at the center of galaxies. He obtained a bachelor degree in mechanical engineering in 2001 at the University of Palermo, Italy, followed by a master's degree in physics at the University of Trieste, Italy, and a PhD in physics in 2007 awarded by the Technical University of Munich, Germany. After postdoctoral research at Stanford University and at the University of California, Berkeley, he joined the faculty at the Clemson University in 2014. Among other awards, Marco Ajello received the South Carolina Governor's Award for Excellence in Research and the Otto Hahn Medal of the Max Planck Society. And Marco is also my supervisor in my graduate study. So today, Marco is going to tell us about the gamma ray emission of galaxy outflows. So Marco, the floor is yours.
Thank you, Shuri. Thank you for the kind introduction. It's great to be here. Thank you, Federico, Shuri, and Emi for inviting me to give this talk. This is a lot of work that we did during the pandemic, and as such, I never had personally the pleasure to give a talk about it. So I'm very excited to be sharing with you a couple of results here. And I will say upfront that most of this work has been done by some of my collaborators, in particular, two of the postdocs here, Chris Carwin and Alex McDaniel, in participation with people at the University of Chicago and some of our Xray experts at the College of Charleston and in Poland. So the motivation for our work starts basically from the detection of an isotropic flux of PeV neutrinos by IceCube several years ago. And the realization, you see it here on the left, that the intensity of the gamma ray background measured by Fermi, the supposedly neutrino background measured by IceCube, and the cosmic rays, particularly the high energy ones, their intensities are all the same or very comparable. So this makes the case for the existence possibly of a class of hadronic accelerators that produce cosmic rays, neutrinos, and gamma rays. And neutrinos are, of course, produced only in hadronic interaction. In this hadronic interaction, roughly, you give as much energy to gamma rays as much as it goes basically neutrinos. So all these neutrino sources should be accompanied by gamma ray sources. So there should be a class of hadronic accelerator out there, but so far we haven't been able to identify that. With the most plausible accelerators, meaning blazars and star-forming galaxies, being nearly ruled out, meaning that the IceCube collaboration has put limits on how much of the IceCube neutrino background can come from these classes, and this is less than 30%. And you see it a little bit on the plot here on the right side, where you see for different source classes, the average neutrino luminosity, from theory, that these sources could have. On the y-axis, you have, the space density in the local universe, and assuming then an evolutionary function. These are these lines here. But basically, you have sources on the bottom right corner, which could be very luminous in neutrinos, but they're also very rare, like blazars. Their space density is very low. On the opposite side of the plot, you have sources that could be very numerous, like low luminous AGN, but intrinsically, they're very weak. And basically, whatever falls in the gray line has nearly been excluded. So BL-LUX, for spectrum nucleoside and BL-LUX has been excluded because otherwise they would have already been seen as point sources by IceCube. Okay, so the idea of this talk is basically to look for potential sources of neutrinos by looking at sources of gamma rays, because if you have neutrino sources, those must also produce gamma rays. So what type of gamma ray sources are out there? The fourth Fermilab catalog of gamma ray source, in particular the DR3 version, which was accepted a couple of days ago, contains roughly 6,600 gamma ray sources, and they have broadly divided them into two types. Sources with a jet, like blazars, radio galaxy, and GRBs, and sources that are known to accelerate cosmic rays. These are in our galaxy, like pulsars, supernova, remnants, star clusters, novae, And then, we detect all this emission or all the emission due to the accelerated cosmic rays in our own galaxy and in other galaxies. So in general, star-forming galaxies. And you can see that the vast majority of sources are detected by the LATA. Gamma rays are blazars. With many, as much as 35% of all the sources still, without an association. This means we don't know what they are, but they are very likely blazars. So most sources have a jet, and we know those really cannot produce the entire amount of the neutrino that we see. And then there are these cosmic ray sources broadly defined. They could to some extent, but not produce 30%. So the idea is that most of the sources that we have already seen cannot really produce much of the neutrino vector that we see. So we need to look for new sources of gamma rays. And that's where we started looking basically for the gamma ray emission from galaxy outflows. So we know that every galaxy, of course, has a supermassive black hole at the center. And from theory, we know that an accreting supermassive black hole can power, can launch wide-angle winds that could be magnetically driven or radiation pressure driven. And these winds are probably observed in several wavelengths, particularly in absorption in X-rays and in UV. And they're called like UFOs, ultra-fast outflows. These are probably the closest to the accretion disk that people have detected. They can have large velocities, meaning a fraction of the speed of light, sometimes even 30% of the speed of light. The UFOs and the broad absorption line in quasars are some of the strongest winds. But then there are, if you move a little bit farther out from the black hole, there are these warm absorbers and narrow absorption lines that they are slower, and these are winds probably generated farther out, or that have propagated farther out. Eventually, all these are AGN-driven winds, and we know this. Then eventually, you go to the scale of the galaxy, and you have these molecular, neutral, and ionized outflows. There could be also AGN-driven winds, but there could be some driving done by the star formation activity of the galaxy itself. And maybe at the end of the spectrum, you have these gigantic bubbles like the ones that we see in our galaxy. Now, these winds have always been believed to be essential for regulating the growth, the coevolution of the galaxy and the supermassive black hole itself. They come technically in two types. They're always the same wind. They could be momentum driven and energy driven, which means that the first type of winds or outflows are actually cooling, and so they radiate, and so they're not very powerful, while the energy driven are energy conserving, they're not cooling, and so they transfer a lot of energy to the interstellar medium. Typically, the line separated into classes is when you have an outflow that's that whose kinetic energy, kinetic power is roughly 5% or more of the bolometric luminosity of the AGN. And this is enough, given enough time to unbind the gas from the galaxy. And so they're powerful enough to unbind the gas from the galaxy. Now, you will believe that such a powerful, fast wind in the interaction with interstellar medium will power a shock, and shocks accelerate particles. And so these are fairly normal things that are seen all the time in gamma rays. And so you will believe that this kind of winds will also generate gamma rays via basically cosmic ray interactions and cosmic ray acceleration and the shock. And so we have looked for the emission. We have actually looked at the opposite end of this phenomena. We have looked for the emission from ultra-fast outflows and the emission from molecular outflows. And so I'm going to start with the first one. Just to remind everyone, UFOs are outflows detected via basically blue shifted absorption line in X-rays that are broad, and they are due to iron K-shell absorption. They imply, these are seen in nearly 30% of all radio loud and radio quiet AGN nearby. So they're very common. They imply that the wind or the outflow is very fast, moving with speeds which are nearly always of the order of 10% the speed of light. a mass outflow rate of up to 1 solar mass per year, and large kinetic powers of 10 to the 42 to 10 to the 45 ergs per second. We don't really know precisely the location of where these winds are launched from, but they are believed to be, launched, to, distances similar as those of the accretion disk itself. There have been some work in the past, in 2016, 17, and 18, predicting that these winds could generate, in fact, gamma rays and neutrinos. And that was the basis, basically, for our search. The predicted luminosity of 10 to the 40 ergs per second, more or less, is very low for an instrument like the Large Area Telescope on Fermi, so they will be undetectable. And so we actually optimized a little bit the search for this kind of phenomena. We selected only 11 systems from the work of Tom Bessie and Gofford, from galaxies that are radio quiet. They're all extremely local and they have a velocity larger than 10% of the speed of light. And, we searched for the emission gamma rays. And of course, the theory was correct. They were too faint. We didn't detect any of them. So we resumed to do a stacking analysis. And in gamma rays, we don't stack photon from different sources, on top of each other. But what do? We scan the likelihood profile for, for the best fit parameter of a given source. And then we add the log likelihood profiles of every source, because the log likelihood is additive. This is equivalent in Xspec to doing a simultaneous fit to different sources, keeping the same free parameters across all the sources. All this analysis is done, above 1 GeV all the way to 800 GeV. And so this is the results for the search for, an average emission from the UFO. It's positive, we detect the average emission of 5.2 sigma. You see here the 1, 2, and 3 sigma contours on, we modeled the spectra with a power law, and so we get a constraint on the photon index and the gamma ray flux. The gamma ray flux is not very important, but the photon index is actually pretty hard for a source emitting, above 1 GeV. And this implies, this typical index of 2 is what you would expect from shock acceleration. This implies that these are good accelerators. Now, in gamma rays, of course, we don't resolve the galaxy, so we don't know exactly what is producing those gamma rays. So the only way we can ascertain that these are related to UFO is by using a control sample. And our control sample is matched in X-ray luminosity and distance. So these are galaxies that are exactly the same, in which people have looked for a UFO but have not found it. And the result of the control sample basically returned no signal. So we are very confident that the emission that we see is due because these galaxies have an active UFO there. And also, this gamma rays cannot be due to star formation because the level of star formation activity is not that high in those galaxies. And so you would expect a signal that's much weaker than the one we find, a factor of 40 or so. And by selection, these objects are all radio quiet, and so they don't have a relativistic jet pointing along our left side. So we are really confident that the emission comes from the UFO. Now, the simple picture is that you have an AGN that's powering a wind. This wind, is a very fast velocity. It's decelerated here at the reverse shock. And then eventually there is the region of the shocked wind, the contact discontinuity that's separated with the shocked ambient gas. And then here you have the forward shock that moves basically through the galaxy. Okay. The picture is rather simple. From theory, you expect that the AGN transfers parts of its volumetric luminosity to the wind in forms of kinetic power to the wind. And you would expect, the more powerful wind would accelerate more, would transfer more energy to the cosmic rays. And that's exactly what we see. And this is shown in these two plots here. So starting from the one in the left, we see that AGN that are more luminous in terms of their volumetric luminosity are also more luminous in gamma rays. So they're powering more cosmic rays, and those are emitting more gamma rays. And this is because, and it is seen on the right panel, basically AGN with a larger bolometric luminosity are powering more powerful winds that have a larger kinetic power, and a fraction of that basically goes into genetic gamma rays. So that's what we expected from theory. Actually, the only, and this is what we see here basically with this green contour CR1 sigma for both relation. And the only actual prediction is the purple dashed line here from the work of Liu et al. That actually had this prediction built in and is actually satisfied. The interesting thing that we measure here is that these UFOs transfer nearly the same amount of power to cosmic rays and gamma rays as star formation activity in these galaxies do. So this means if you imagine a UFO to be active for a few million years, then there will be enough energy transferred to cosmic rays as there is from normal star formation activity. And so UFO can really energize a large fraction of the cosmic ray population. Now, what we did, following the model, is basically we modeled the emission from cosmic ray, the acceleration and emission from cosmic rays and protons and electrons accelerated at the shock front. We find that the emission of the electrons, or the electronic emission, is never able to explain the gamma ray that we see. And this is because it is always too faint and always too soft. It's never as hard as the spectrum that we measure, which is basically flat in a UFO representation. So the emission must come basically from the protons, and indeed the protons are able to explain the emission, and the best fit is here. But basically this is done by tracking, the acceleration of cosmic rays at the shock front. You see here the red line shows you basically the gamma ray emission due to the protons, how it varies with time, from the onset, say, of the AGN activity to eventually when the wind basically runs out of material to interact with. And so we believe that we're mostly seeing these sources at the peak. And so when the wind has traveled probably tens of parsec from the launch location region. There are two interesting things that are seen from the model. One is that these outflows can actually accelerate protons to large energies, 10 to 17 electron volts, which are enough to produce, the neutrinos that we will see from Xscale. Although this is just a theoretical inference, because the highest energy photon that we measure is 300 GeV, and this will correspond only to protons of, say, 3 TeV or so. Okay, so if you want to find the photons which are basically generated together with the neutrinos, you need to look at photons around 10 TeV. And so you need to wait for CTA to become online and be able to detect these sources. Okay. The second thing is that only a little bit of the energy goes actually to the cosmic rays. Most of the energy goes to the thermal heat of the plasma, inflating a large bubble, and you transfer to this bubble basically 10 to the 15 ergs in roughly a couple of million years, which is in agreement. Basically this means, this kind of outflow would have no problem inflating structures like the Fermi and Rosetta bubbles. All right, in the last few minutes, I'm going to talk about the molecular outflows now. We are using a sample which is provided by Fleury et al. In 2020 and 2019. It's mostly from ALMA observation of CO transition. And we rely on 30 objects at redshift less than 0.2. Again, these have incredibly large mass outflow rate and also a very large range of kinetic power. Also, these ones are detected at 4.4 sigma and always with a very flat index. Okay. Here, the situation is a little trickier because every single galaxy that has a molecular outflow also has a lot of star formation activity. And we know star formation activity produces gamma rays. So the control sample here is matched in distance, but also in total infrared luminosity, which is a tracer of star formation activity. And also these are galaxies for which ALMA has not found a molecular outflow. So these are galaxies that have possibly the same level of star formation activity at the same distance, but no molecular outflow. And again, there is no gamma emission associated with that. So we are confident that the gamma emission comes from this galaxy because the molecular outflow is there. We also know that the signal comes entirely from those outflows that are in an energy dream regime. So where basically the kinetic power is larger than 5% of the AGN bolometric luminosity. So these are the strongest outflows, and those are the most interesting ones. And also comes mostly from galaxies that either don't have an AGN or have a very weak AGN. So these are not necessarily AGN-driven outflows. It could be due to the starburst emission in these galaxies. We try to do a similar exercise as we did for the UFOs and try to correlate the gamma emission that we see with properties of the outflow, like the mass outflow rate or the kinetic power of the outflow. And all the searches returned a null result. This means that we have no proof whatsoever that the molecular outflow is doing any acceleration. Indeed, we find something different and also very interesting, and it's shown here on the plot on the right. This shows basically the gamma ray luminosity versus the total infrared luminosity, which is a tracer star formation. You should focus here only on two lines, basically the green shaded contours and the yellow one. The green contours are normal star-forming galaxy, okay, where there is no evidence, for an outflow. The yellow ones are the ones with a molecular outflow. What we find is that for a given level of star formation or total infrared luminosity, the galaxy with an outflow have an excess gamma emission with respect to those that don't have it have star formation activity. And moreover, we find that the ones with an outflow occupy the regions where basically sources that are purely calorimetric exist. And the calorimetric limit is basically determined, assuming that all the protons accelerating supernova explosions release their energy within the galaxy without escaping. So basically, in short, what we find is that galaxies with a molecular outflow produce more gamma rays simply because they are better target for cosmic rays, accelerated probably in supernovae explosions. Okay, so before going to the summary, I'll just remind that these are the three people that work the most in these projects. Chris Carwin, a postdoc here, work mostly on the UFO paper. Alex is working on the details of the molecular outflow paper. And Rebecca Deasing, who is a PhD student at the University of Chicago, basically backed all of that with theory. So the summary is that we have found two new sources of gamma rays. These are sources, galaxies that have a UFO, galaxies that have a molecular outflow. This was expected from theory, and we've been very happy to verify that. We found proofs that the UFOs are accelerating particles directly. They could technically accelerate them to very large energy, but this needs to be confirmed by other instruments. For molecular outflows, we haven't found the proof, but we all found that molecular outflows or galaxies with a molecular outflow are nearly perfect calorimeters. So on one side, for the neutrino emission, which is a better neutrino emitter, you have an accelerator on one side and an accelerator on the other one, which is also a very good target, to absorb those protons. And so my bet, my money is mostly on the molecular outflow, simply because you need a thick target, for absorbing the protons and generating neutrinos. And so I'll leave you with this slide, and thank you for this opportunity.
Thank you, Marco. Is there anyone has a question for Marco? Also in the Zoom. So maybe, Marco, I have a question. So could you comment more on what's the difference between the UFO and the molecular outflow? I mean, what makes them different?
Yes, I mean, it's both the detection ways, and so UFOs are highly ionized. Let's see, highly ionized outflows that attain X-rays, and they come from presumably very close to the accretion disk. Molecular outflows are detected basically in CO, so these are different phase. They are detected at the kiloparsec scale, in the galaxy, They're even seen by eye, you know, in the image of M82 here, for example. You see here, that's the molecular outflow that you see from the galaxy.
Thank you, Marco.
So.
So I think we are good here. So let's thank the speaker again. Thank you, Marco. See you next week.
Thank you. See you soon.